Okay, I again continuing the video. Sorry for the interruption. So I erased this portion of the board and I put down our polynomial down there. Okay, so we found that the Galois group of K over Q, its number of elements, divides 6. And well, this number of elements of the Galois group is the same as the degree of K, the splitting field of a polynomial, over Q. So what's that degree? So let alpha be a root. By the way, this is a degree 3 polynomial with coefficients in Q. From calculus, any polynomial of degree odd with coefficients in the real numbers, it will have a real root, right? Because if you think about what happens as x goes to plus or minus infinity, on one side it's going to go to minus infinity, on the other side to plus infinity. So there's always going to be the degree is odd, it will have at least one real root. So we could take alpha to be that root, but for now let's just keep it general. Let's just say a root of f. But later we're going to take this to be the real root. Okay, so now what does our diagram look like? You've got Q adjoint alpha, and then K, the splitting field. Now, okay, so what's this degree? Because alpha is the root of f being the reducible of degree 3, that degree is 3. So this has degree 3. And then on the other hand, what we've seen here is that the number of elements of the Galois, which is the same as the degree of that extension, that is divides 6. So this is 3. This is either 1 or 2. This is 1 or 2. Right? And because this whole thing divides 6. Okay, very good. So the question is, which case are we in? Now, this particular polynomial that we started with, so up to here, everything we said is valid for any irreducible polynomial of degree 3. Now, that specific polynomial that we're looking at, let's see, okay, so what's the derivative of f? F prime x is 3x squared plus 1. The derivative on all of the real numbers is positive. F is increasing on the real numbers. So you see that, we already knew that it has at least one real root, but because it's increasing, it can't have more than one root. It must have exactly one real root. So f odd degree, together with it being increasing, implies that f has exactly one root in R. Okay, so there's one real root. So let's say alpha is the real root. Alpha, took it to be a root. Let's say alpha is the real root. So let suppose alpha is the real root. Suppose alpha is the real root. Okay, there's two more roots, beta and gamma, the other two roots. The three roots are distinct, right? Because it's reducible and separable. Okay, so these are the other two roots. Now, so think about this. Think about complex conjugation. Complex conjugation fixes the coefficients of f, fixes Q, and hence the coefficients of f. So let's say phi from C to C be complex conjugation. Well, it fixes all the real numbers, in particular all the rational numbers. This is an element of the Galois group of C over Q. And then because of that, because it fixes Q, it's an automorphism of C that fixes Q for any polynomial with coefficients in Q, phi will permute the set of roots of that polynomial. The set of roots of that polynomial in C. So sigma permutes roots of f or any polynomial with coefficients in Q. By the way, when I say roots of this, I mean the roots in C, right? These are roots in C. So sigma permutes the roots of this polynomial. Okay, so now sigma sends, well, the real root is getting mapped to itself, and then you've got these two other roots, which are beta and gamma, which are not real. Well, those two guys, well, because complex conjugation permutes alpha, beta, gamma, well, it fixes alpha, so it has to, well, permute beta and gamma, but because beta and gamma are not real, it doesn't fix them, so it has to swap them. Sigma fixes alpha, doesn't fix beta or gamma, so sigma must, so on the set of roots alpha, beta, gamma, sigma acts like, well, it's the permutation beta gamma. Like in particular, what you see is that these beta and gamma are complex conjugates of each other. Okay, so sigma on the set of roots on alpha, beta, gamma acts like beta, gamma. But now, okay, so here's a question for you. Does sigma give us an element, so does sigma restrict to an element of the Galois group of K over Q? Right? Sigma is an automorphism of C, which fixes Q, and the question is, did I change my name? Did I change the name of my yeah, the complex conjugation? My apologies. So the complex conjugation, I started calling it phi, but then I changed it to sigma, right? So if you don't mind, I'm just going to change this to sigma. So sigma is the complex conjugation. We saw that on the setup of roots of f, it's the permutation that swaps the two non-real roots, beta and gamma. Now, the question is, well, does sigma restrict to an element of the Galois group of Q over Q? If it does, then, well, so you've got complex conjugation. This complex conjugation, well, an element of the Galois group, K over Q, it's an element of order Well, it acts like this permutation. Right? It's an element of order 2. An element of order 2. The order of sigma is 2. Right? Because it's this permutation, beta gamma. And then if you have an element of order 2, then what does that tell you about the Galois group? If the group has an element of order 2, what does that tell you about the order of the group? Exactly, by Lagrange's theorem. The order of every element divides the order of the group. So if you found an element of order 2, that implies that the Galois group, the order of the Galois group must be a multiple of 2. So by Lagrange's theorem, what you would get is that by Lagrange, two divides the order of the Galois group. And now combine that with the possibilities for the order of the Galois group that you already have. So far we knew that the order of the Galois group was either 3 or 6. Right? It was a multiple of 3 and a divisor of 6. Put that together with the fact that the order is even, you'll see that the Galois group here, it must have 6 elements. It must be the full permutation group, the full symmetric group on the set alpha, beta, gamma. This is equal to the full symmetric group on the set of roots of f in this case. That is assuming that sigma, so complex conjugation, does indeed restrict to an element of the Galois group of K over Q. So the exact same argument in general, if you have an irreducible polynomial of degree 3 over Q, polynomial of degree 3, which is irreducible over Q, well, there's going to be two situations. Either it has exactly one real root, which is what we have here, or it can have 3 real roots. If it has 2 real roots, it's forced to have a 3rd real root too. So either it has exactly 1 real root, or all its roots are real. If it exactly has 1 real root, so the other 2 roots now are going to be complex conjugates of each other, just like here. And then, if we can argue, which we're going to come back to this in a second, if we can argue that complex conjugation gives an automorphism of the splitting field of the polynomial over Q, then the Galois group will be exactly the full symmetric group on the set of roots of the polynomial. So let me stop this video here and come back with another video.